In this video, we're gonna study the first test for series. This thing is called the integral test. The integral test will be used to test the series when you have its term to be positive. So its terms must be positive in this case, and the thing that the integral test come from turned out to be this picture. This picture, you see that you have f is a continuous function. Okay, so you have f is a continuous function, positive non-increasing function. So it's going to be the function that is turned out to be like going down like this one. And you have an equal to fn. Okay, so it's going to be an equal to fn. Let me highlight the color. So you have an equal to fn. And you see from this picture that you have the term A2, okay? So A2 will be just the height here, okay? So let me, so this one you see that it's gonna be F2, okay? So F at 2. And you see this guy, the height is equal to F at 3. So let's see some dotted line like this one. Okay, so you see F3, F4, and you see that the thing that you have here is gonna be the area. So if you consider the area of this one, it's gonna be the height, which is F2 equal to A2 multiplied with the width. The width is equal to 1. So when you have the height equal to A2 and the width is equal to 1, the area here turned out to be equal to A2. So this one is the area. Okay, so you have the area equal to A2, and the area for the second bar is A3, and area for the third bar turned out to be A4 respectively. And you can have this one is A2, this one is A3, and so on. So for us, so it's going to be going down, okay? And if you sum the area, so you see that if you have A2, A3, A4, you're going to miss something. You're going to miss some error here. And what is the thing that you miss is going to be, you see that the whole thing is going to be the area under the curve y equal to fx from 1 to infinity. Okay, so this guy is going to be from 1 to infinity, and this one is going to be y equal to fx. And you see that you have a2, a3, a4, and an, and so on. So this one is going to be, you get the first inequality. So the first inequality gives you in this way that you have the sum from n equal to 2 to infinity must be less than this integral from 1 to infinity of fx. Okay, so this one is mean that, let's take a look at this picture. Okay, so it's mean that you have the sum here, which is this guy, and it's turned out to be the sum on the left side, and the integral is going to be bigger. So it's going to be bigger because it includes some error. Okay, so in this case, it's going to be the integral from 1 to infinity of fx dx. However, if you add a1, okay, so if you add a1, so you have a1 also, it's going to be a1, a2, a3, a4. So you see that you're going to get something extra. Okay, so you're going to get something extra. So that leads us to the second term. So it's going to be the pink one, and the pink one turned out to be, give you the second inequality. Okay, so the first one is the green one. So the green one gives you the first picture. Okay, the second one is the pink one. The pink one gives you the second picture, and it's going to give you two inequality that you can see. Okay, so from here you can compare these two terms. Okay, so if you compare this guy, if this guy conversion, okay, so if this guy convergence or this guy finite, this guy is also conversion. Okay, so if this guy convergent is turned out to be convergent, so this guy come directly from the green one. So it's going to be, I'm going to just use color to like distinguish what we are proving so far. Okay, so it's going to be, this guy is come from the green one. However, if you have this guy divergent, so if you have the thing that smaller turn out to be infinity, this guy also divergent. Okay, so this one, if this guy's divergent turn out to be infinity like this guy also infinity, and it's turned out to be divergent as well. So that will turn out to be the second color. Okay, so that will be the conclusion. So the thing that called integral test mean that in order to test for conversion of the series, we're gonna just test for the conversion for the improper integral instead. This one, integral from 1 to infinity that we studied last semester turned out to be useful in order to test the conversion. However, it's gonna be difficult to integrate a little bit when you have the complicated an. So we may have to use other tests instead. If you have the function or an in terms of the one that you feel that it can be integrated, for example, like 1 over n squared plus 1, like this one that you know that we be able to integrate, or it's going to be log root n over n like this, that you be able to integrate as well. So you may just use the integral test. However, we're going to have some restriction that require before we can use the integral test turn out to be, you must check that an always positive. So you must have an positive term, and you have it is decreasing. Okay, so it's going to be decreasing sequence, and in the form that it's going to be in the form of the function that we can integrate. Okay, so it's going to be many requirement here. So the first one is going to be positivity. The second one will be decreasing. And the third one is going to be the form that we be able to manage or we be able to integrate. Okay, so that will be the thing that you gonna have to use. So let's recognize something. So you have the integral conversion, you have the series conversion. If you have the integral diversion, the series also diversion. Okay, so that is called the technique of the integral test. Okay, so this guy is called the integral test. Okay, so let's do 3 examples. The first one for doing this guy is gonna be, you're gonna try to use integral test to determine whether the following series is conversion or diversion. Okay, so you have the series n equal to 1 to infinity of 1 over n squared plus 1, and this one will be your an. Okay, so this one will be your an. So you have an equal to 1 over n squared plus 1. Okay, so this guy, you see that is positive. Okay, so this guy is always positive. So you gonna check the first one that you have an positive for all n. Okay, so this one taking care of the positivity. The second one, you check decreasing. Okay, so the second one, you're gonna check decreasing. The way to check decreasing, I told you that you can use direct comparison or you can just differentiate this one. So for this one, let direct comparison. So you have, we know n is less than n plus 1. Okay, so you have n less than n plus 1. So you have n square must be less than n plus 1 square. So you get n square plus 1 less than n plus 1 square plus 1. And this guy turned out to be, you need this guy on the bottom. So you flip this one down. So it's going to be 1 over n squared plus 1. It's going to be more than 1 over n plus 1 squared plus 1. And this is an. This is an. And this is an plus 1. Okay, so you see that you have decreasing. Okay, so it is decreasing. Okay, so you already checked two things. So you have the series that you have turned out to be the sequence AN that you have turned out to be decreasing, and it's going to be positivity. So the third step turned out to be you need to integrate. Okay, so let me resize this one a little bit. So you're gonna integrate, so that will be our last step. So the third step here, okay, so the third step here gonna be you gonna integrate 1 to infinity, and when we integrate, we normally familiar with variable x, so let's change n to x, so it's gonna be 1 over 1, not 1, x squared plus 1 dx. Okay, so we have integral from 1 to infinity of 1 over x squared plus 1 dx. So if you recall from Calc 1, this guy turned out to be limit t go to infinity, integrate 1 to t of 1 over x squared plus 1 dx. Let me recall you what I did. The thing that we have here is calculus 1, that when you deal with integrate from 1 to infinity like this, you're gonna change this guy into integrate 1 to t, and you are taking t to infinity. So this is the definition. Okay, this is the definition. It's not trick, so it's gonna be the definition of this improper integral. So this guy is called improper integral. If you not recall, try to like go back to the previous clip on calculus 1 on this topic, and it's going to be help you recall this one, and you just need only type 1. Okay, so this one is going to be type 1 improper integral. And you see that this integral that you're gonna compute first turn out to be integrate, so it's gonna be arc tan x. Okay, so integrate 1 over x squared plus 1 is turned out to be arc tan x, and it's gonna be from x equal to 1 to x equal to t. So this one will be arc tan t subtract arc tan 1, okay, and you are taking limit t go to infinity, Okay, so you are taking limit t go to infinity. So you see your t here, your t here. Okay, and this guy turned out to be finite because it turned out to be arctan infinity minus arctan 1, and arctan infinity is pi over 2 and arctan 1 is pi over 4. So it's going to be pi over 2 minus pi over 4. So this guy is going to be pi over 4. Okay, so that will be the thing that we have. Okay, so you have this guy turn out to be pi over 4 conversion. Okay, so we know that our improper integral turn out to be conversion. So we're gonna conclude that we have the series n equal to 1 to infinity of 1 over n squared plus 1 is conversion. Okay, and that's all. Okay, so that will be our first example. The second example is going to be you have log root n over n. Okay, so for this example, you have an. Okay, so you have an equal to log root n over n. So you need to check positivity. Okay, since n more than 1, okay, so you have log n more than log 1 is equal to 0, okay, and you have log root n, okay, so let me just put root n, sorry. So you have this one, so you have root n is more than 1, so you have log root n more than log 1, so it's turned out to be 0, okay, and you divide by n, so it's turned out to be 0, okay, so you have an is positive, okay, so that will be just the first step. The second item that we need to check is going to be decreasing. For checking decreasing, this one is going to be, you'll not be able to do the direct comparison because you're going to have the quotient. So it's not be possible to have like the comparison that allow us to do like in the previous case because here you have n on top and on the bottom. So we're going to differentiate. Okay, so check decreasing. We're going to have fx equal to log root x over x, okay? And you have x greater than or equal to 1, okay? And we're gonna differentiate f prime x. Before I differentiate this guy, let's make our line a little bit easier. So this one, you can just write this one as, okay, so for this one, it's gonna be, you have 1/2 log x over x, okay, so it's gonna be 1/2 log x over x. So it's gonna be 1/2, and you differentiate log x over x, you use the quotient rule. So it's going to be the bottom derivative of the top minus the top derivative of the bottom over the bottom square, And you see that this guy turned out to be 1 minus log x over 2x squared. And you see that the bottom guy, okay, so the bottom guy here is positive. Okay, so this bottom guy here is positive, and you have x more than 1. This guy is negative. Okay, so this guy is negative. Okay, so in this one, so you have this guy is negative because if you plug in, okay, it's not negative for any x, so it's going to be x negative for, let's say, x more than 3. Okay, so if you have x more than or equal to 3, it's going to be negative, and that's good enough because we can just get rid of like a first two term. So this one is going to be, you see this term first, you see this term first. However, it's going to be like the first two term that the sequence is not less than 0. However, if you continue the third term, the fourth term, the fifth term, and so on, it's going to turn out to be decreasing. So that okay for using integral test. So you see that you may have problem with the first two terms that sometimes look like this, okay? However, for the other term, it's gonna become smaller, smaller, smaller like this one. So when we do the series test, we just ignore this two term, okay? So you can just ignore this two term, and you see that we can apply the integral test to the rest of the term here, okay? So it's gonna be, you can start at n equal to 3, okay? N equal to 3, n equal to 4, n equal to 10 or something. So it's gonna become smaller and smaller, so you have decreasing, okay? So you get this one, so the sequence turn out to be log root n over n is decreasing. Okay, so we be able to conclude decreasing. However, it's going to be decreasing eventually. It's not going to be decreasing all the time. It's going to be decreasing eventually in this case. The last thing that we're gonna do is gonna be, we gonna integrate. Okay, so the third step that we gonna do is gonna be, we're gonna integrate from 1 to infinity of log root x over x dx. So this one will change by the definition to be limit t go to infinity from integrate 1 to t, and like I did earlier, so I can write this one as log x over x dx, and you have 1/2 on the bottom. Okay, so you have 1/2 on the bottom. And then you're gonna just perform the substitution. So let's integrate this one by just use the substitution. So we're gonna let u to be, let's make this guy a little bit smaller. Okay, so we're gonna do the substitution by letting u to be log x, okay? And we have du to be 1 over x dx. And this will become 1/2, okay? And it's gonna be u du, okay? And it's gonna be integrate. So you have x equal to 1, u equal to log 1 equal to 0, and x equal to t, u equal to log t. Okay, so it's going to be 0 to log t. And for this one, you gonna integrate. Let me highlight some color to give you some guideline. Okay, and so for this one, it's gonna be integrate u, so it's gonna be 1/2 2u square from 0 to log t. Okay, and you would get 2 cancel, so it's gonna be log t square, okay, minus 0 square, and you're gonna take limit t go to infinity. Okay, so that I copy from the first line, and you take to this log t. Okay, so it's gonna be log t. Okay, and you have this one is gonna be infinity. Okay, because log infinity turned out to be infinity. So in this case, you get diversion. Okay, so you get diversion. So the conclusion from 1, 2, and 3, you're gonna have the series n equal to 1 to infinity of log root n. Okay, so of log root n over n is diversion. Okay, so it's gonna be that. Okay, so this is how we do this example. So you see that it's gonna always consist of 3 steps, okay? And it's gonna turn out to be the conclusion here that you have diversion, okay? So you have this integral diversion. So it's turned out to be series also diversion. If you have the integral turn out to be conversion, you have the series is conversion. Okay, so that will be the thing that you have. For the next one, okay, for the next one, you see it's 1 over n log n. So the thing that you can see first is going to be this one is a little bit different from the previous one due to you have n equal to 2, not n equal to 1. And we have n equal to 2 because you have log n here. If you have n equal to 1, it's going to be 1 over 0, so it's undefined, so we not be able to have that. So we're going to have to start from n equal to 2 to infinity. The thing that is going to be different turn out to be when you do the integral at the third step. Okay, before I do the integral at the third step, let's do the first and the second step. So you have the first step, you know that since n is more than 1, you have log n more than or equal to log 1 equal to 0. So you can multiply them together. Okay, so you have this yellow guy and this yellow guy multiply to each other, so you get positive. Okay, positive multiply positive turn out to be positive, and you flip this one up, so you have an equal to 1 over n log n is positive. Okay, so that will be the first step. The second step, okay, so the second step, you're gonna check for decreasing. For decreasing here is gonna turn out to be you gonna check decreasing. So we're gonna check decreasing by just direct comparison. Why? Because you have n only on the bottom. If you have n only on the top or n only on the bottom, you don't need to differentiate. It's gonna follow quite simple. And it's gonna be just you have n more than n less than n plus 1, and you have log n less than log of n plus 1. So from this step, you're gonna have n log n. So you have this guy multiplied together, and you have this guy multiplied together. So you have the blue guy multiply with the blue guy, and you have the purple guy multiply with the purple guy. So you get n log n less than n plus 1 log n plus 1. Okay, so you have the blue guy multiply with the blue guy, and you have the purple guy multiply together. And you flip these two number out, so it's going to be 1 over n log n more than 1 over n plus 1 log n plus 1. Okay, so this one will allow you to conclude that you have your an and you have your an plus 1. Okay, so this one is your an. Okay, and so you have that the sequence turn out to be decreasing. Okay, so you have your sequence turn out to be decreasing. Okay, let me move this one. Okay, so you have number 1 and number 2 ready. You must have something like this. Okay, so you must have number 1, number 2 is going to be graded, and you're going to get point for doing something simple like this one. Okay, the hard part for the integral test turn out to be on the test itself. So you're gonna do the integrate. So the third step here is gonna be you're gonna compute integral. Okay, like I told you, it's gonna be you're gonna start at 2. Okay, so you're gonna start at 2, so it's gonna be 2 here. Okay, because of the pink guy that you see from the series, so it's gonna be 2 to infinity of 1 over x log x dx. Okay, I'm gonna let you do this one on your own first. I'm gonna give you the complete solution during the recitation, and this one turned out to be limit t go to infinity, and it's gonna start from 2 to t of 1 over x log x dx. Okay, and you're gonna just use the substitution. So you're gonna let u to be log x, okay? And you complete this one to see whether you get conversion or diversion, okay? And we're gonna complete this one during the recitation. Okay. The next one is your example 20th here. So we like to find the value of P for which the series is conversion. Okay, so we like to check whether this guy is conversion or diversion. So we gonna consider this series in several cases. The thing that we see here that the parameter that we are studying turn out to be parameter P here. Okay, so the parameter that we are studying turn out to be, we like to find the value of P. So the parameter P that we're gonna have. So we're gonna distinguish the case according to the parameter P. So for P equal to 1, okay, for P equal to 1, the series become the series n equal to 1 to infinity 1 over n. Okay, so this one is the harmonic series. Okay, so this one is the harmonic series and it is divergent. Okay, so this is what we learned in the previous lecture. So it's turned out to be divergent and it is because it is harmonic series. The next case when we have P, when P negative, okay, so when you have P negative, the series n equal to 1 to infinity of n to the p is divergent. Okay, so it's turned out to be divergent because if you consider limit n go to infinity of 1 over n to the p, and this p turned out to be negative. Okay, so this p turned out to be negative. So it means that you have n to the negative. Okay, so this guy will be equal to limit n go to infinity of n to the minus p. Okay, so it is equal to n to the minus p, and this minus p turned out to be positive. Okay, so this guy turned out to be positive when you have minus sign in front. And you see that this one will become infinity. So this one will become infinity, and it's become infinity because it is infinity to positive. Infinity to positive is turned out to be infinity. Okay, and you have the limit equal to infinity, so your series turned out to be divergent. Okay, the next one, okay, when you have p positive, not p positive, so when p equal to 0, when p equal to 0, your series become 1 over n to the 0, so it's going to be series n equal to 1 to infinity of 1, okay? So this guy is divergent. This guy is divergent for sure because it means that you have 1 plus 1, 1 plus 1 plus 1, infinite term, okay? So infinite term. So it's turned out to be divergent. Okay, so it's turned out to be divergent. So we have like 3 cases already. Now we're gonna assume that p greater than 0 and p not equal to 1. Okay, so we're going to assume that p greater than 0 and p not equal to 1. We shall use the integral test. Okay, so we use the integral test. Okay, so we use the integral test. So in order to apply the integral test, we must check number 1, number 2, and number 3. Let's do number 1. Number 1, we know that an equal to 1 over n to the p, always positive. Okay, so it's quite very clear because the bottom here is positive. Okay, nothing to do much. Number 2, okay, number 2, you're gonna check for decreasing. So you have n is less than n plus 1, okay? So you get n to the p smaller than n plus 1 to the p positive, okay? And you flip this one, so you get n to the p higher than n plus 1 to the p. So this guy will be your an, this guy will be your n plus 1. Okay, so it's going to be an more than an plus 1. So it is decreasing. Okay, so it is decreasing. Okay, so it is decreasing. The third step will be, so the third step will be you need to integrate. So we're gonna compute integrate from 1 to infinity of 1 over x to the p dx, okay? And this guy will be limit t go to infinity of integrate 1 to t of 1 over x to the p dx. So this one we use the limit definition in order to deal with this improper integral, okay? And then what? And then you just basically integrate this guy. So it's gonna be integrate 1 over x to the p not equal to 1, okay? P not equal to 1, so it's gonna be just x to the minus p plus 1 over negative p plus 1 from 1 to t. So it's gonna be 1 over negative p plus 1, okay? And you're gonna multiply with t to the negative p plus 1 minus 1. And you use limit t go to infinity. Okay, so you use limit t go to infinity. Okay, I make this guy a little bit smaller. And then you see that it will depend on negative p plus 1, okay? If negative p plus 1 positive, okay, so if negative p plus 1 positive, it's gonna turn out to be infinity, okay? So I'm gonna conclude that it's turned out to be infinity if negative p plus 1 positive. Okay, if negative t plus 1 positive is turned out to be positive, okay, and if you have negative p plus 1 negative, it cannot be 0 because p not equal to negative, p not equal to 1, okay, so p not equal to 1, so you're gonna have only 2 cases. And it's gonna turn out to be some number, so it's gonna be 0, so it's gonna be 1 over, so it's gonna be negative 1 over negative p plus 1, okay, so it's gonna convert to one number. Let's see this one. Negative 1 over negative p plus 1. Okay, so it's turned out to be a finite number when you have negative 1 plus p is negative. So this condition will mean that you have p smaller than 1. Okay, when you have p smaller than 1, and this guy you have p greater than 1. Okay, so this guy is p greater than 1. Okay, So this limit turned out to be, let me explain this guy again. So when you have this guy negative, it becomes 0 because it's turned out to be 1 over infinity. It's going to turn out to be 1 over infinity, and this guy go to 0. Okay, that's why I left with this term. However, when you have this guy positive, it will lead to infinity for this term. So it's turned out to be diversion for that case. Okay, so let me highlight this one and this one for you to see. Okay, so this one is the third case. And you can conclude from this calculation that okay, so we be able to conclude from this calculation that the series n equal to 1 to infinity of 1 over n to the p turn out to be conversion, okay, and it's turned out to be diversion. Depend on, okay, so depend on p less than 1 or p greater than 1. So conversion, okay, if you have p more than 1, and if you have p less than or equal to 1, it's gonna be diversion. Okay, one thing that you may have here is due to you are assuming, okay, so due to you are assuming p positive, okay, so you are assuming p positive. However, we have diversion for these 3 cases also, okay, so you can combine, okay, so you can combine with this green case, okay, so this one is the green case. So you see this one is p positive, okay, this one is p positive, p less than 1, okay, and p negative, p equal to 0, p equal to 1 can be combined into the green case as well. So this one is my green case, okay. Another of my case is going to be my pink case. My pink case is conversion, okay, so that will conclude everything. So this form of series is called P series. The letter P that you see here is a parameter. Okay, so the letter P that you see here is a parameter. And it's turned out to be conversion if you have P positive more than 1, okay, P more than 1, and it's turned out to be diversion if P less than or equal to 1. So this one will give you many advantage. For example, if I ask you series 1 over root n equal to 1 to infinity, series n equal to 1 to infinity, n over to the third, like this, and series n equal to 1 to infinity of 1 over n to the pi, and series n equal to 1 to infinity of n to of the third root of n, okay, something like this. So you're gonna just determine conversion or diversion by identifying P, okay? So here you have P equal to 1/2, okay? So you look at P is gonna be the parameter that you're gonna use to determine conversion or diversion. So for this guy, you have P equal to 3, okay? And this guy, you have P equal to pi. and this one you have p equal to negative 1/3. Okay, so that the parameter p from each series, okay, here is going to be p equal to 1/2 because this one is going to be n to the 1/2. Okay, so it's turned out to be that parameter. And so you're gonna answer conversion or diversion. Okay, so for conversion or diversion, it's going to be p equal to 1/2. It's going to be less than 1. Okay, so it's diversion. P more than 1 is conversion. Pi is more than 1, so it's conversion. And negative 1/3 is less than 1, so it is diversion. Okay, so this one is about the P series, and P series will be used a lot when we do the next section about the comparison test. Okay, so today it's going to be just you have to recognize the parameter P and you just memorize the pink guy and the green guy. Okay, so that's all. Okay, I left you one example here, okay, that you please complete this one and we're gonna see the solution during the recitation. Okay, so that's all for this video.